everybody, welcome back to Trigonometry. Today we are looking at section 6.2 and just a little bit of section 6.3, and we're going to be solving trigonometric equations. In this section we'll talk about how to solve trig equations using linear methods, how to solve using the zero factor property method, and how to use trigonometric identity substitutions to solve certain types of trig equations. So here we go. So solving trig equations involves isolating a single trig function and then using inverse trig functions to find all the values that make that equation true. A lot of times the equation will specify that you just need to give all solutions in the interval from 0 degrees to 360 degrees, or they might say from 0 radians to 2 pi radians. Solutions in this interval are called principal solutions because those are all the solutions in the first complete rotation around the coordinate system. Now, whether they say 0 degrees to 360 degrees or 0 radians to 2 pi radians, that interval will tell you whether your solution should be stated in degrees or radians. Of course, any angle that is coterminal with one of the principal solutions is also a solution. So later on, we will talk about how to write the set of all solutions of an equation. But we're going to start by solving equations that can be solved using linear methods. So trig equations that are linear in form have only one trig function, and it will be to the first power. To solve an equation that's linear in form, just isolate the trig function and then you'll either determine the solutions using memorized function values and ASTC, or you can use an inverse function on the calculator to get a reference angle and then use ASTC to determine the final solutions. We're going to see examples of both of these coming up. So here's example 1, and it says solve the equation 2 sine x plus 1 equals 0 for exact solutions over the interval from 0 to 2 pi. Now we notice here that they asked for exact solutions, so that tells us that we should be able to do everything based on our memorized values, and we should not be having to reach for the calculator. And then the interval that they gave us here, 0 to 2 pi, tells us that we're expected to state the solutions in radian form. So here is our equation, and we want to isolate the sine of x. So to do that, we're going to subtract 1 from both sides, and that will eliminate the plus 1 from this side, and we'll have a negative 1 show up on the right side. So that would give us 2 sine x equals negative 1. And now we want to eliminate this coefficient of 2 by dividing both sides by 2, and that will leave us with sine of x equals negative 1/2. Now there are two quadrants where sine values can be negative, so that would be quadrant 3 and quadrant 4. So we're going to have a solution in each of those quadrants. From memory, I know that the sine of 30 degrees is 1/2, so we can label this reference angle as 30 degrees and also this reference angle as 30 degrees. Now the solution is the standard position angle. So for this quadrant 3 angle, the solution would be 180 plus 30. So that quadrant 3 angle is 210 degrees. And this fourth quadrant solution is going to be 360 degrees minus 30, which is 330 degrees. Now remember, we're supposed to state exact solutions over the interval from 0 to 2 pi. So we need to take these two solutions and convert them to radians. We know that 210 is 7 times 30. And we know that the radian equivalent for 30 degrees is pi over 6. So 7 times 30 degrees becomes 7 times pi over 6 radians. And 330 is 11 times 30. So this 330 degrees converts to 11 pi over 6 radians. And once we find all the solutions, we will always state our solution set inside curly braces. So now we're going to say x equals curly braces 7 pi over 6, comma, 11 pi over 6. Now here's just a note about entering these answers in My Math Lab. They will typically have the variable name and the equal mark and the curly braces already on the screen for you, and all you're supposed to do is type your solutions inside the curly braces. So you would type 7 pi over 6, comma, 11 pi over 6, and that's all you would need to type. Now, while we're here, let me also remind you that you can get this pi symbol in my math lab by typing the letters pi, and it will convert to the pi symbol for you. And you can get a fraction bar by just typing the slash key, the one that shares a button with the question mark. So if you type 7 pi slash 6, you will get this 7 pi over 6 fraction. And then to type the comma, you would want to hit the right arrow to move your cursor outside of that fraction, because otherwise the next thing you type is going to go in the denominator. So you'll hit the right arrow key, then your comma button, and then you can type 11 pi slash 6, and that will give you your second solution, and you'll be done. Now, we were able to get exact solutions on that one because 1/2 was one of our memorized sign values, but it doesn't always work out that way. So if a trig function is not equal to one of our memorized values, then we'll need to use the inverse trig functions on the calculator to find approximate solutions. So this is where decimals can get involved. Before you start working on the calculator, make sure to set your calculator in degrees or radians as needed. And remember that the calculator is only going to give you the one solution that fits the rules for the inverse function that you're using. But this answer may not be a solution to your equation, and even if it is, there may be other principal solutions that you need to find. So anytime you use the calculator, you will actually use the calculator's answer to help you find the reference angle, and then use that information together with ASTC to find the other principal solutions. And now let's look at example 2 together. So part A says, solve the equation 3 cosine theta plus 1 equals -1 for approximate solutions over the interval from 0 degrees to 360 degrees. Round solutions to 1 decimal place. So let's start off by copying our equation. And of course our strategy is to isolate this cosine theta. And we start by subtracting 1 from both sides. And that's going to give us 3 cosine theta equals -2. And then to isolate the cosine theta, we'll divide both sides by 3. And so now we know that cosine of theta equals -2/3. Now this is not one of our memorized cosine values. So to get the values for angle theta, we will have to write this in inverse form. So let's say that cosine inverse of -2/3 is equal to theta. And now go to your calculator, make sure that it's set in degrees, and you'll type in cosine inverse of -2/3 equals, and you get a calculator answer of approximately 131.8 degrees. Now if you look at our equation here, we should be expecting a solution in every quadrant where cosine is negative, and that would be quadrant 2 and quadrant 3. And the calculator did give us a quadrant 2 answer, but we also know that there's a solution in quadrant 3, and the calculator is not going to give us that answer. We have to find it on our own. So what we're going to do is use the 131.8 to find the reference angle here. This reference angle would be 180 minus 131.8, so that would be 48.2 degrees. And that means that the reference angle on the other solution is also 48.2 degrees. So the quadrant 3 answer is 180 plus 48.2 degrees, and that's 228.2. So for this equation, our two solutions are 131.8 degrees and 228.2 degrees. Now, when you type this in MyLab, you will not need to type the degree symbol, because the instructions will say enter your answer in degrees, and therefore they assume that whatever number you type, you're typing in degrees. But do be aware of how many decimal places you're supposed to keep. The instructions here said round to 1 decimal place, but they might not always say that on every equation. So be sure to read the instructions underneath the answer box to know for sure how many decimal places you're supposed to round to. And here is part B of example 2. It says solve the equation -2 cotangent x equals 5 for approximate solutions over the interval from 0 to 2 pi radians. Round the solutions to 2 decimal places. So let's go ahead and write down our equation. And we know that we want to isolate the cotangent of x. So let's divide both sides by -2. And now we have cotangent of x equals -5/2. Now this is not the cotangent value for any of our memorized reference angles. So we know that we're going to have to use the calculator on this. And we also knew that because it said approximate solutions. So we know decimals are involved. Let's go ahead and use the reciprocal identity for cotangent to write this as tangent of x equals -2/5. Notice I left the negative in the top because there's no sense moving it to the bottom. It's always better to keep a negative in the top of a fraction. And now let's restate this in inverse form. So if the tangent of x is -2/5, that means the tangent inverse of -2/5 is x. And we are about to get the calculator to evaluate this for us, but we have to make a choice at this point because remember, we've got to state the solutions in radians, but it's much easier to visualize and think in degrees. So what I would suggest for you to do is leave your calculator in degree mode, and that way you'll know that you're getting answers that are in the right quadrant, and then we'll convert those solutions into radian form. Okay, so going to the calculator now, tangent inverse of -2/5 gives us -21.8 degrees on the calculator. Of course, this cannot be a solution to our equation because we want the solutions between 0 and 2 pi radians, or in degrees it would be the solutions between 0 degrees and 360 degrees. This -21.8 degrees is not in the correct interval. So what we will do is just use this as the reference angle. So the reference angle for all of our solutions is going to be 21.8 degrees. Now we need to decide what quadrants our solutions should be in. So if the tangent of each solution is a negative number, then we're going to have a solution in each quadrant where tangent values are negative. So that would be quadrant 2 and also quadrant 4. And the reference angle for each of these solutions is 21.8 degrees. So this reference angle right here is 21.8 degrees, and that makes the standard position quadrant 2 angle 180 minus 21.8 degrees. So that's 158.2 degrees. And then this reference angle is also 21.8 degrees, and that makes the fourth quadrant solution 360 minus 21.8 degrees, which is 338.2 degrees. So those are our two solutions in degree form, but remember that we're supposed to state the solutions in radian form. So now we need to convert each of these. So 158.2 degrees times pi over 180 gives us approximately 2.76 radians. And for the quadrant 4 answer, 338.2 degrees times pi over 180 gives us approximately 5.90 radians. So now to state the solution in curly braces, we'll have 2.76 comma 5.90. And remember that the order of the solutions is not important. As long as you have both solutions in there and they're both correct, you're in good shape. Now you know how to convert between degrees and radians on the calculator. So the way we just did it was to take the 158.2 and multiply by pi over 180. And when you do it this way, it doesn't matter if your calculator is in degrees or radians, because the calculator doesn't know that we're dealing with angles, as a matter of fact, because we're not using any trig functions. However, instead of multiplying by pi over 180, there is a way to get the calculator to convert for you, and here's what you would do. To get the calculator to convert 158.2 degrees into radians, we'll need to set the calculator in radian mode. So you'll hit the DRG button and go over to radians and hit equal. Okay, now notice that the calculator screen says RAD, so we know we're in radian mode. If I enter the 158.2 and use my degrees, minutes, seconds button to specify to the calculator that this number is in degrees, then when I hit equal, it will convert to radians for me. So that's just another option for you. Now, not every equation has a solution. There are equations that have no solution, and that's okay. Another way to say that an equation has no solution is to say that the solution is the empty set. And the symbol for the empty set is a circle with a line through it. It kind of looks like a 0 with a line through it. So here is example 3, and let's see what we can do with this one. It says solve the equation 3 cosecant theta plus 6 equals 5 over the interval from 0 to 360 degrees. So let's start by writing down our equation, and now let's isolate the cosecant theta. We'll start by subtracting 6 from both sides. That will give us 3 cosecant theta equals -1. And now we divide both sides by 3, and that gives us cosecant theta equals -1/3. Now this cosecant value does not match any of our memorized reference angles, so we know we're going to have to go to the calculator. So let's switch into sine form. So let's rewrite this using the reciprocal identity for cosecant, and then we would have sine of theta equals the reciprocal of -1/3, which is -3. Okay, now you may see the problem right now. Sine values must always be between -1 and +1. Therefore, there is no angle that has -3 as its sine value. So we could know right here that this equation has no solution. But let's pretend for a second that you didn't even notice that it said -3 here, and so you haven't noticed the problem yet. So the next thing you would normally do is switch into inverse form, and then you would have sine inverse of -3 equals theta. Now when you enter that on your calculator, the calculator will say domain error. And what that means is -3 is not a number that can be plugged into the sine inverse function. And so because the calculator is unable to give us a solution here, we know that no such theta exists, and therefore we could say that theta is the empty set, or the solution to this equation is the empty set. Now let's talk about principal solutions versus all solutions. Now it makes sense that for any equation, if an angle is coterminal with a principal solution, then that coterminal angle is another solution. And therefore, if an equation has at least one solution, then technically it has an infinite number of solutions. So if we're asked to state all solutions of an equation, it's impossible to list them all. And so instead, for each principal solution, we'll write an expression that can be used to calculate all the angles that are coterminal with that solution. If we're supposed to state the solutions in degrees, then we can take each principal solution and write plus 360 degrees in after it, where n is any integer. But if we're working in radians, then we would write each principal solution plus 2 pi n, where n is any integer. By writing the solutions this way, we're giving whoever is reading our work a formula that they can use to calculate as many solutions as they want. So if you have any principal solution, you can add 360 times 1 to get another solution. Or you could add 360 times 2 to get yet another solution. And as many times as you want to plug in a new value for n, you can calculate a new solution to your equation. So let's look at example 4 together. It says solve the equation 2 secant x plus 1 equals secant x plus 3 for all exact solutions in radians. So notice this time it doesn't say give the solutions between 0 and 2 pi. It says give all exact solutions. So we do still have to start by finding the principal solutions, but it's not enough to just list the principal solutions. Now we need to provide a little expression that can be used to calculate all of the exact solutions. So let's start by writing down our equation, And of course, we want to isolate the secant of x. Now notice here that we have a secant term and a constant term on the left. We also have a secant term and a constant term on the right. Whenever you have both kinds of terms on both sides of the equal mark, you probably already know that the easiest way to solve this is to eliminate the smaller variable term. So I'm going to subtract secant x from both sides. On the left, 2 secant x minus secant x leaves secant x, and then we have our plus 1. And on the right, secant x minus secant x goes to 0, and we just have 3 remaining on the right side. Now let's subtract 1 from both sides, and we have secant x equals 2. Now we didn't really memorize secant values for our reference angles, so let's get this in a reciprocal form. If the secant of x is equal to 2, we know that the cosine of x will be equal to 1/2. And although you can use the calculator for this, you really shouldn't have to, because you should recognize this as one of our memorized cosine values. We know that the cosine of 60 degrees is 1/2, so 60 degrees is our reference angle. Now we also notice that this cosine value is positive, and we know that cosine is positive in quadrant 1 and quadrant 4. So our two solutions are going to come from quadrant 1 and quadrant 4, and they each have a reference angle of 60 degrees. That means the quadrant 1 solution is 60 degrees, and the quadrant 4 solution will be 360 minus 60, which is 300 degrees. Now remember that the problem asked us to state all exact solutions in radians, so we need to convert each of these principal solutions into radians. 60 degrees we know is pi over 3 radians, and 300 degrees is 5 times 60, which is 5 pi over 3 radians. So to state all solutions, we would say x equals curly braces pi over 3 plus 2 pi n, comma, 5 pi over 3 plus 2 pi n, where n is any integer. Now let's shift gears a little bit and talk about equations that are nonlinear in form. So if there's more than one trig function involved, or if there's a squared trig function, then we say that the equation is nonlinear in form. And to solve an equation that is nonlinear in form, you will need to either factor or use identities to make substitutions, or very often both. Now you remember from algebra that solving a quadratic equation by factoring involved moving all the terms to one side of the equal mark, because you had to have equals 0 on the other side of the equal mark. So you move all the terms to one side of the equal mark first, then you factor, and once the trig functions are separated into separate factors and the other side of the equal mark is 0, then we'll use the zero factor property to solve. And that's just the idea that if one factor times another factor equals 0, that tells you that one of the factors is 0. So if a times b equals 0, then either a equals 0 or b equals 0. So here's example 5, and it says solve the equation, parentheses, cotangent x plus 1, close parentheses, times, parentheses, square root of 3 cotangent x minus 1, close parentheses, equals 0 over the interval from 0 to 2 pi. So this time we're only required to state the principal solutions, but we do need to give the solutions in radians. So the factoring in this equation is already done for us, and we just need to say that since this parentheses times the other parentheses equals 0, it means that one of the parentheses has to equal 0. Therefore, we want to find all values of x that would make the first parentheses equal 0, and we want to find all values of x that would make the second parentheses equal 0. So let's take the first factor. If cotangent x plus 1 times something else equals 0, it might be that cotangent x plus 1 equals 0. So let's subtract 1 from both sides, and that would give us cotangent x equals negative 1. And therefore the reciprocal is true. If cotangent x equals negative 1, then tangent of x also equals negative 1, because negative 1 is its own reciprocal. Now 1 is one of our memorized tangent values. So we know that a tangent value of 1 means that the reference angle is going to be 45 degrees. And since this tangent value is negative, we're going to have a solution in each quadrant where tangents are negative. And so that would be quadrant 2 and quadrant 4. And again, we have a 45 degree reference angle. So the quadrant 2 solution is going to be 135 degrees, and the quadrant 4 solution is going to be 315 degrees. And we remember that we're going to have to convert these to radians, but we'll just wait and do that at the end. Let's take the other factor now. So if this first parentheses times the second parentheses equals 0, it might be that the second parentheses equals 0. So we want to find all values of x that make that second parentheses equal 0. Let's start by adding 1 to both sides. So we'll have square root of 3 cotangent x equals 1. And then divide both sides by square root of 3. And we have cotangent x equals 1 over square root of 3. Now your first reflex might be to rationalize here, but notice that this is cotangent, so in order to figure out what's happening, we're going to want to change into tangent form. So the reciprocal of cotangent x is tangent x, and the reciprocal of 1 over square root of 3 is square root of 3. Now that we see it in this form, we know that square root of 3 is one of our memorized tangent values. This tangent value tells us that the reference angle will be 60 degrees. And since this tangent value is positive, it's going to give solutions in quadrant 1 and quadrant 3. Those are the quadrants where tangent is positive. And again, the reference angle is 60 degrees, so the quadrant 1 solution is 60 degrees. The quadrant 3 solution is going to be 240 degrees. Now let's convert each of these into radians. 135 is 3 times 45, so that would be 3 pi over 4. Now you might remember that way back in chapter 3 we talked about an easy way to convert whenever you have a 45 degree reference angle. Remember, 45 degrees is just half a quadrant, so we can count half quadrants here. 1, 2, 3 half quadrants means this angle is 3 pi over 4. And then 1, 2, 3, 4, 5, 6, 7 half quadrants means that 315 degrees is 7 pi over 4. It's very convenient to convert that way when your reference angle is 45 degrees. It's not as convenient when your reference angle is something else. So for the quadrant 1 angle, we just know that 60 degrees is equal to pi over 3. And for the quadrant 3 angle, we know that 240 degrees would be 4 times 60, which is going to be 4 pi over 3. And so our 4 solutions all together are 3 pi over 4, 7 pi over 4, pi over 3, and 4 pi over 3. Now the equation in the last example was already factored for us, but most of the time we'll have to do our own factoring. So just a reminder, to solve by factoring, we always start by putting all terms on the same side of the equal mark. That's because we need to have one side of the equation equal to 0 so that we can use the zero factor property to finish the solving process. So here's example 6, and it says solve the equation sine of x times tangent of x equals sine of x over the interval from 0 to 2 pi. Now notice here that we have two different trig functions, and they are in the same term. That is, they form one term together. So we're not going to be able to isolate either sine of x or tangent of x the way we have in the previous examples. Instead, we're going to need to factor here, which means that we're going to have to move this sine of x term over to the left side of the equal mark. So if we subtract sine of x from both sides, we will have 0 on the right side and minus sine of x on the left side. So that would give us sine of x times tangent of x minus sine of x equals 0. Now notice that we have two terms here, and these two terms have something in common. They both contain sine of x, which means that sine of x can be factored out as a GCF. In other words, we can undistribute the sine of x. So if I do that, I'll have sine of x times some parentheses. And the question we have to ask ourselves now is, what do we need in the parentheses so that distributing sine of x would produce this original expression again? So we can say sine of x times tangent of x would produce this term, and then we would have a minus sign, and then we need sine of x times 1 to produce this term. And now at this point, a lot of students leave this as it is and go on to the next step. But remember, the next step is to say that since sine of x times this parentheses equals 0, then one of the factors must be equal to 0. But I don't have anything here telling me that this factoring equals 0. So the equals 0 must be copied from the previous line. You can't set each factor equal to 0 unless the whole factored expression is equal to 0. So do not lose your equals 0 here. That's a bad habit that a lot of students have, and that is something that can count off. So make sure as you're solving that you keep your whole equation together. Okay, now we have sine of x times this parentheses equals 0. So we say, since this equals 0, either sine of x equals 0 or tangent x minus 1 equals 0. And we'll solve that in a minute, but right now let's work with sine of x equals 0. So if sine of x equals 0, that means that the terminal side goes through a point where the y coordinate is 0. That would happen at 0 degrees, and it would also happen at 180 degrees. See, any point on the terminal side for these two angles would have a y coordinate of 0. Now let's take the other factor and set it equal to 0. So if tangent of x minus 1 equals 0, that means tangent of x equals 1. Now for an angle to have a positive tangent value, that angle would have to be either in quadrant 1 or quadrant 3. So we're going to get a solution from each of these quadrants. 1 happens to be one of our memorized tangent values, and that tells us that the reference angle for each of these solutions is 45 degrees. Now for the quadrant 1 angle, of course the solution is 45 degrees. For the quadrant 3 angle, the solution would be 225 degrees. And now, because they asked us to state the solution set in radians, we'll have to convert each of these 4 solutions to radians. So 0 degrees is equal to 0 radians, 180 degrees is equal to pi radians, 45 degrees is equal to pi over 4 radians, and 225 is 5 times 45, so that would be 5 pi over 4 radians. But also remember, because the reference angle is 45, we can just count half quadrants. So 1, 2, 3, 4, 5 half quadrants also gives us 5 pi over 4. And so now to write the solution in set notation, we say x equals curly braces 0, pi over 4, 5 pi over 4. Now before we go on to our next example, I want to show you a very common error so you'll know how to avoid it. A lot of students notice that we have sine of x on the left and sine of x on the right, and they say to themselves, well, if I just divide both sides by sine of x, then the sine of x's will cancel out from both sides and I'll have tangent of x equals 1, and they get the two solutions pi over 4 and 5 pi over 4 from this equation. And as you know, this solution set is missing 2 of the solutions, and the reason is they got lost when we divided by sine of x. So what you want to keep in mind is that you should never divide both sides by a variable or a function that contains a variable. So right here, the problem is that we divided by sine of x, which contains a variable, and that causes a loss of solutions. So instead of dividing to separate trig functions, always separate them by factoring. Okay, so here is example 7, and this one says solve the equation -2 sine squared theta equals 3 sine theta over the interval from 0 to 360 degrees. Now again, this one is nonlinear in form because we do have a squared function here. So we're going to be doing some factoring. Now for myself, if I have a squared term, I always prefer for that squared term to be positive because the factoring just seems more natural that way. So what I'm going to do is move this negative 2 sine squared theta over to the right side of the equal mark. And that's going to give us 0 equals 2 sine squared theta plus 3 sine theta. So notice again that both terms contain a sine of theta, so that can be factored out. It's like reversing the distributing process. So we would have 0 equals sine of theta times some expression in parentheses. So we have to ask ourselves, sine of theta times what would give us this term? And we would need sine of theta times 2 sine theta to produce this term. Then we have a plus sign. And sine of theta times 3 would produce this term. And so you can always check mentally, just see if you can distribute what you factored out and get back to your original expression. And of course we would. So now, since sine of theta times this parentheses equals 0, one of these factors has to be 0, and we have to find what values of theta make each factor 0. So first we want to find out what would make sine of theta equal 0, and then in a minute we'll find out what makes 2 sine theta plus 3 equal 0. Now we saw sine of theta equal to 0 in the last example, so we already know that sine of theta will equal 0 when theta equals 0 degrees or when theta equals 180 degrees. And for the second factor, if 2 sine theta plus 3 equals 0, then we want to isolate the sine of theta here. So we'll move the 3 to the other side of the equal mark. That would give us 2 sine theta equals negative 3. And then we would divide both sides by 2, and that would leave us with sine of theta equals negative 3 over 2. Now we already know that all sine values have to be between negative 1 and positive 1, and this number is not between negative 1 and positive 1, so this is not a valid sine value, and therefore no such angle exists, and this factor produces no solutions. Now don't worry if you didn't notice that negative 3 over 2 was not a valid sine value, because if you switch this into inverse form and enter it in your calculator, you would have to enter sine inverse of negative 3 over 2, and it would give you a domain error, and then you would know, this factor just did not produce any solutions. But this other factor did produce 2 solutions. So we would say that our solution set is 0 degrees and 180 degrees. And let's look at example 8 together. So this one says solve 3 sine squared theta minus 2 equals 5 sine theta for all solutions in degrees. Round approximate solutions to 1 decimal place. Okay, now as I start to think about what approach to take to solve this equation, I notice that I have a sine squared theta here. So that tells me that this equation is nonlinear in form, and that tells me that there's probably going to be factoring involved. So I know that I'm going to have to bring all the terms to one side of the equal mark, so I'm going to take this 5 sine theta and move it to the left. Now if you're thinking ahead a little bit, you'll notice that this needs to be the middle term of our trinomial here, because I've got a squared term and then a term that's to the first power and then a constant. So this should remind you of a quadratic equation like the ones you saw in algebra. So we're going to have here 3 sine squared theta minus 5 sine theta minus 2 equals 0. So here's a trinomial, and we know that when we factor a trinomial, it factors into 2 binomials. So we're basically reversing the FOIL process. I'm going to go ahead and write my 2 empty pairs of parentheses here. And now we know that 3 sine squared theta can be written as 3 sine theta times 1 sine theta. So we'll fill in the first term in each parentheses. And then last times last made a minus 2. So the minus tells us that these signs are going to have to be different, but we don't know, of course, which way we should put them down. You just need to put down a minus and a plus. If they are in the wrong spots, we will know later that we need to change them when we check the middle term. The 2 can only be formed by 1 times 2. So we'll put 1 and 2 here. And now we don't know if these numbers are in the right place or if these two signs are in the right place until we check the middle term. So outer plus inner should add up to negative 5 sine theta. If we check, outer times outer makes 6 sine theta, and inner times inner makes minus 1 sine theta. 6 sine theta minus 1 sine theta would be positive 5 sine theta, but we wanted it to say minus 5 sine theta. So the fact that the sign is wrong tells me that my signs here are in the wrong place. If I just switch the signs, then everything works fine. Outer times outer now is minus 6 sine theta, and inner times inner is plus 1 sine theta, and those two do add up to minus 5 sine theta. So now our factoring is correct, and we can go ahead with the rest of the equation. Notice here I've got my equals 0 right here, because you don't want to lose the equals 0, because now we need to be able to say, since this factor times this factor equals 0, one of the factors must be 0. So we have to find what values of theta cause each factor to equal 0. Either 3 sine theta plus 1 equals 0, or sine theta minus 2 equals 0, but we'll handle that in just a minute. For 3 sine theta plus 1 equals 0, we want to isolate sine of theta, so we'll move the plus 1 to the other side of the equal mark. That will give us 3 sine theta equals negative 1, and then divide both sides by 3, and now we have sine theta equals negative 1/3. Now, of course, this is not one of our memorized sine values, so we do have to get the calculator involved here. So let's write this in inverse form, and that would be sine inverse of negative 1/3 equals theta. If you plug sine inverse of negative 1/3 into your calculator, you will get that theta equals negative 19.5 degrees. Of course, this is not one of our principal solutions because it's not between 0 and 360, but we can use it as the reference angle for our solutions. Now, what quadrants will our solutions be in? Well, sine is negative in quadrant 3 and quadrant 4. So if sine of theta is a negative number, we're going to have a quadrant 3 solution and a quadrant 4 solution. Now, for each of these, the reference angle is 19.5 degrees. So for quadrant 3, with a reference angle of 19.5 degrees, the solution there would be 199.5 degrees. And for the quadrant 4 solution, with a reference angle of 19.5 degrees, the quadrant 4 angle would be 340.5 degrees. Now let's take the other factor and set it equal to 0. So if sine of theta minus 2 equals 0, that means sine of theta equals 2, but we know that sine values have to be between negative 1 and positive 1, and this number is not, so that means that no such theta exists, and this factor did not produce any solutions to our equation. So the only two principal solutions that we have are 199.5 degrees and 340.5 degrees. But remember that we're supposed to state all solutions in degrees. So for each one of these, we need to not just list the principal solution, but an expression that can be used to generate any coterminal angle for each of these solutions. So our final answer would be that theta equals 199.5 degrees plus 360 degrees times n, comma, 340.5 degrees plus 360 degrees times n, where n is any integer. Now here in example 9, I want us to get just a little more practice factoring because I find that's a little bit of a hang-up for a lot of students. So this one says solve 2 secant squared theta plus secant theta equals 10 over the interval from 0 degrees to 360 degrees, round approximate solutions to 1 decimal place. Now the first thing I notice is that I have a squared function here, and that tells me that factoring is going to need to be involved. And so I know I need the other side of the equal mark to have a 0. So the first thing I'm going to do is subtract 10 from both sides, and that would give us 2 secant squared theta plus secant theta minus 10 equals 0. Now notice that we have three terms here, so when we factor we will be reversing the FOIL process, and that means we're going to start off with two empty pairs of parentheses. Now 2 secant squared theta would break down into 2 secant theta times 1 secant theta. Last times last produced minus 10, so in order to get the minus we're going to need the signs here to be different. It doesn't matter how you put them down, just put down two different signs. And then last times last had to make a 10, so I have two choices here. I could either use 2 times 5 or 1 times 10. In case you don't know, what you should do is pick one pair of numbers, put those two numbers in the empty slots that you have, and check your outer plus inner. If you don't get the middle term that you're looking for, then you can reverse the position of those two numbers, and if that doesn't work, then you try the next pair of numbers. So for us, we're going to start with 2 times 5, and I'm just going to put them down like this and see what happens. So outer times outer would be minus 4 secant theta, inner times inner would be plus 5 secant theta, and negative 4 plus 5 does add up to positive 1. So our middle term would be plus 1 secant theta, which is what we have here. So that tells me that our factoring is correct. All right, now we can say since this factor times this factor equals 0, one of the factors has to be 0, and it's our job to find out what values of theta make each factor equal 0. So if 2 secant theta plus 5 equals 0, then we want to isolate the secant theta. So we'll move the 5 to the right side of the equal mark. That gives us 2 secant theta equals negative 5. And now divide both sides by 2, and we get secant theta equals negative 5 over 2. Now this is not one of our memorized values, so we know that we're going to end up with some approximate solutions here. But we can't go to inverse form just yet because we don't have an inverse secant button on our calculators. So we need to switch this into cosine form using a reciprocal identity. So if secant theta is negative 5 over 2, then cosine theta is negative 2 over 5. And that means cosine inverse of negative 2 over 5 equals theta. Now we can get a number from the calculator for this. If you punch cosine inverse of negative 2 over 5 into your calculator, you will get theta equals 113.6 degrees. And now we know that there are two quadrants where cosine is negative, but the calculator is only going to give us this one solution. So what are the two quadrants where cosine values can be negative? Well, that would be quadrant 2 and quadrant 3. Now, the quadrant 2 answer is the one the calculator gave us. That's the 113.6 degrees. But before we can figure out the quadrant 3 answer, we need to know the reference angle, which we can figure out from the quadrant 2 answer. So the reference angle here would be 180 minus 113.6, so that would be 66.4 degrees. So that reference angle also applies here. And now we can see that the quadrant 3 solution is going to be 246.4 degrees. Now let's take the other factor. And so secant theta minus 2 could also equal 0. And that would mean that secant theta equals 2. And of course we want to switch into cosine form here. So if secant theta equals 2, then cosine theta equals 1 over 2. And this is one of our memorized cosine values. This 1/2 tells us that we're working with a reference angle of 60 degrees, and because it's positive, we know that we're going to get a solution in quadrant 1 and another solution in quadrant 4. Now the quadrant 1 solution is 60 degrees. The quadrant 4 solution has a reference angle of 60 degrees, which means that solution is 300 degrees. And so now we have 4 solutions here, 2 of them exact and 2 of them approximate. But the problem asked us for the principal solutions in degrees, so we don't have to convert anything to radians. We just have to list them all in the curly braces. So now we have theta equals curly braces 113.6 degrees, comma 246.4 degrees, comma 60 degrees, comma 300 degrees. Now let's look at part B of example 9, and it says solve cotangent squared theta plus 9 equals 5 for all solutions in radians. Round approximate solutions to 2 decimal places. So again, here we have a squared function, but this time there's not another term that contains a trig function. So let's solve this one using the square root property, which you might remember from algebra. So to use the square root property, we isolate the squared term, and so we'll do minus 9 on both sides of the equal mark, and that will give us cotangent squared theta equals negative 4. Now we apply the square root property, which means we unsquare the left side. That would give us cotangent theta. And then on the right side, we'll have plus or minus square root of whatever's over here. So that would give us plus or minus square root of negative 4. Now, a negative under a radical is going to produce an imaginary number, but we know that every angle has a cotangent between negative infinity and positive infinity, so those numbers are all real. So it's not possible to find an angle that has an imaginary cotangent. Therefore, no such theta exists, and this equation has no solution, or we could say that theta equals the empty set. Now, just in case using the square root property might not have been your first thought, let's approach this by factoring. So if we want to factor, we'll need a 0 on one side of the equal mark. So this time, let's do minus 5 on both sides of the equation. And that would give us cotangent squared theta plus 4 equals 0. Now we can try to factor this, so let's go ahead and write down our two sets of parentheses and see if we can reverse the FOIL process. So first times first has got to be cotangent theta times cotangent theta. Last times last made plus 4. So we would need to have two of the same sign here. So let's go ahead and put here plus 2 and plus 2. Now let's check the factoring and see if it produces this expression. So first times first would be cotangent squared theta. Outer times outer plus inner times inner would give us 4 cotangent theta for our middle term, and last times last makes plus 4. So we do get our cotangent squared theta and our plus 4, but we've got this middle term, which is not supposed to be here. So we know that this factoring is wrong. Let's try again. What if we make the signs different? Well, we can get rid of the middle term by changing one of the signs to minus, but now when we try the FOIL process again, this time we get cotangent squared theta minus 4. So there's no way to have the plus 4 and yet not have a middle term. So there's no way to factor this. And since it won't factor at all, your next step would have to be the square root property, or as a last resort, the quadratic formula, but we will not be using the formula in this class. Now, sometimes before you factor, you have to make an identity substitution. So if there are two different trig functions in the equation, but no way to factor, then you will need to make an identity substitution. The goal with a substitution is always to be able to write the equation using only one trig function, or to be able to separate the functions by factoring so that you only have to deal with one trig function at a time. So let's see what happens here on example 10. It says solve 2 tangent x minus 6 cotangent x equals 0 over the interval from 0 to 2 pi. Now notice that we have tangent x in this term and cotangent x in another term, and so we can't separate them by factoring because they're not in a multiplication type setup. So what we're going to have to do is use a reciprocal identity to replace cotangent x in the top with tangent x in the denominator. That would give us 2 tangent x minus 6 over tangent x equals 0. And now you might say, well, that's great that we got rid of cotangent and now the only function we have is tangent of x. But now the problem is that tangent of x is in the denominator, and you're right, we do have to get that tangent x out of the denominator. So let's multiply both sides of the equation by tangent of x. Now when we distribute tangent x on the left side, The first term will be tangent x times 2 tangent x, which is 2 tangent squared x. Then we have a minus. The second term will be tangent x times 6 over tangent x. And the tangent x in the top will cancel the tangent x in the bottom, and that will just leave minus 6 for our second term. And then on the right side, 0 times tangent of x is still 0. Now here we are back in the same position that we were in on part B of example 9. We have a squared trig function and no other terms that contain trig functions. So let's try again solving by square root property. To do that, we'll need to isolate the tangent squared x on one side of the equal mark. So let's add 6 to both sides. That will give us 2 tangent squared x equals 6. And now let's divide both sides by 2. Then the 2's on the left side of the equation will divide out, and that will leave us with tangent squared x equals 6 over 2, which is 3. So we have tangent squared x equals 3. Now, to isolate tangent of x, we apply the square root property. So we unsquare the left side, that would give us tangent of x. And on the right side, we have plus or minus square root of whatever's on the right side. So that would be plus or minus square root of 3. Now this is one of our memorized tangent values. So now we're going to be able to find exact solutions. We're going to get solutions for when tangent of x equals positive square root of 3 and solutions for when tangent of x equals negative square root of 3. So let's think about quadrants first. When tangent of x equals positive square root of 3, we're going to find a solution in quadrant 1 and another solution in quadrant 3 because those are the quadrants where tangent can be positive. And then we know that the square root of 3 is the tangent value for 60 degrees. So the reference angle for each solution will be 60 degrees. In quadrant 1, that means the solution is 60 degrees. And for our quadrant 3 solution, if the reference angle is 60 degrees, then that solution is 240 degrees. Then when tangent of x equals negative square root of 3, we will get a quadrant 2 solution and a quadrant 4 solution. And again, they will each have a reference angle of 60 degrees. That would make the quadrant 2 solution 120 degrees, and that would make the quadrant 4 solution 300 degrees. Now we're supposed to state these solutions in radians, so now let's convert each solution to radians. 60 degrees is pi over 3. 240 degrees is 4 times 60 degrees, so that's 4 pi over 3. 120 degrees is 2 times 60 degrees, so that's 2 pi over 3. And 300 degrees is 5 times 60 degrees, that would be 5 pi over 3 radians. And so now to write our solutions in the curly braces, we have x equals pi over 3, comma, 2 pi over 3, comma, 4 pi over 3, comma, 5 pi over 3. And again, the order that you put the solutions in does not matter. I happen to put them in order from smallest to largest, but you could put them in any order and they would be considered equally correct. Now here is example 11, and this one says solve cosine squared x equals sine squared x plus 1 over the interval from 0 to 2 pi. So again, we have this problem where we have a cosine term and a sine term, and there's no way to isolate these functions by factoring because they belong to different terms that have nothing in common. So instead, what we should do is try to think of an identity that we could use to make a substitution that would eliminate one of these trig functions. Now, the first thing that comes to mind for me is that these terms are both squared trig functions. And so that makes me think of the Pythagorean identities. And so one thing we could do is focus on using our Pythagorean identity that says sine squared x plus cosine squared x equals 1 to eliminate this sine squared x. You know that if you take your Pythagorean identity sine squared x plus cosine squared x equals 1 and you rearrange it so that the sine squared x term is isolated, that would give you sine squared x equals 1 minus cosine squared x. So I'm going to replace this sine squared x term with 1 minus cosine squared x. That will give us cosine squared x on the left equals 1 minus cosine squared x plus 1 on the right. So you can see how 1 minus cosine squared x took the place of sine squared x because they are equal. Now we can think about collecting our cosine squared x terms on one side of the equal mark. So let's add cosine squared x to both sides. That would give us 2 cosine squared x on the left side, and on the right, 1 plus 1 is 2. Now since both sides contain a 2, why not divide both sides by 2, and that will eliminate the 2's and leave us with cosine squared x equals 1. And again, we have an opportunity to use the square root property. So let's unsquare the left side. That would give us cosine x equals plus or minus square root of the right side. So cosine x equals plus or minus square root of 1. Well, we know that the square root of 1 is 1. So now we have cosine x equals plus or minus 1. So we're going to get a solution when cosine x equals positive 1. And we're going to get another solution when cosine x equals negative 1. Okay, so when cosine x equals 1, we're talking about a quadrantal angle. So we're looking for a point on the unit circle where the x coordinate would be 1. Well, that only happens one place, and that is at 0 degrees, and that would also be 0 radians. And then for cosine of x equals negative 1, we're looking for a point on the unit circle where the horizontal coordinate equals negative 1, and that can only happen here at 180 degrees, which is equal to pi radians. So here we only got 2 solutions. That would be 0 and pi. And here we are at example 12. This one says, find all exact solutions in radians. 2 sine x plus 1 equals cosecant x. Well, again, notice that we have 2 different trig functions and they cannot be separated by factoring because they are in terms that have nothing in common. So what we're going to do is use a reciprocal identity to restate cosecant of x as 1 over sine x. So that would give us 2 sine x plus 1 equals 1 over sine x. Now to eliminate sine of x from the denominator here, let's multiply both sides of the equation by sine of x. When we distribute sine of x on the left side, we're going to get 2 sine squared x plus 1 sine of x. And on the right side, sine of x divided by sine of x leaves us with just 1. Now this equation contains 3 terms, and one of them is squared. That tells us that we're going to have to solve by factoring a trinomial. In order to do that, we will need to have 0 on the right side of the equation. So let's subtract 1 from both sides. That will give us 2 sine squared x plus sine x minus 1 equals 0. And now since we have 3 terms here, we know that if this can be factored, it will factor into 2 binomials. First times first is 2 sine squared x. That's going to have to break down into 2 sine x times 1 sine x. Last times last made a negative number. That tells us that the signs in our parentheses will have to be different. Just put down 2 different signs, and if you need to change them, you'll know later. Okay, then last times last is 1. And we know the only way to get a 1 here is to have 1 times 1. Now let's check the middle term. So outer plus inner should add up to plus sine of x. Let's see if it does. Outer times outer gives us 2 sine x. Inner times inner gives us minus 1 sine x. 2 sine x minus 1 sine x does add up to plus 1 sine x. So we're doing really well here. This factoring is correct. Now, since this factor times this one equals 0, one of them would have to be 0. So we're going to need to find out what x values make this factor equal 0, and then what x values make this factor equal 0. Now, to find the solutions for the first factor, if 2 sine of x minus 1 equals 0, that means 2 sine x equals 1. and then divide both sides by 2, and we'll have sine of x equals 1/2. Now, since this sine value is positive, and sine values are positive in quadrant 1 and quadrant 2, we know we're going to get a solution in each of those quadrants. This 1/2 is the sine value for 30 degrees. So now we know the reference angle for both of these is 30 degrees. That means the quadrant 1 solution is 30 degrees, and for the quadrant 2 solution, if the reference angle is 30 degrees, then the quadrant 2 angle is 150 degrees. For the second factor, if sine of x plus 1 equals 0, that means sine of x equals -1. So we're looking for any point on the unit circle where the y-coordinate equals -1, and that can only happen at 270 degrees. Now they did ask for all exact solutions in radians here, so we will translate each of these into radians as we go, and because they asked for all exact solutions, we know that we will have to add plus 2 pi n to the end of each principal solution. So our solution set is 30 degrees, that would be pi over 6, and then plus 2 pi n to get all the coterminal angles, comma, 150 degrees, which would convert to 5 pi over 6, plus 2 pi n to include all the coterminal angles, comma, 270 degrees, which would convert to 3 pi over 2, and then we add 2 pi n to include all the coterminal angles. So these are all the exact solutions for this equation, stated in radians. And then don't forget to add where n is any integer, so that it's clear to people that when they're using these expressions to calculate more solutions, the n that they plug in has to be an integer. Now we've reached section 6.3, and the only thing new here is that we're going to have double angle arguments. And we can't solve with those double angles in place. So before we start solving, we must remove the double angle argument by making an identity substitution, just like we did in the last couple of examples, only now we will be using the double angle identities that you have on your formula sheet, the ones we talked about in section 5.5. Now you'll remember that cosine of 2a had 3 different identities. We had 3 versions of that identity. So whenever you're working with cosine of 2a and you need to make a substitution, you'll have to choose one of those identities, and the one that you want to choose is the one that gets your equation down to just one function. So here's example 1, and it says solve cosine of 2x equals negative sine x over the interval from 0 to 2 pi. Well, you see what's different here from our previous examples is that we've got cosine of 2x. So we've got to deal with that. And the way to deal with it is to replace cosine of 2x with one of its identities. Now, if you look back at your formula sheet, you'll see that one of your identities is cosine squared x minus sine squared x. If I put cosine squared x minus sine squared x here, then yes, that would get rid of the 2x problem, but it would create a new problem because then I would have a cosine term where all my other terms contain only sine of x. But you do have one choice that will allow you to eliminate cosine of 2x and use only the sine function to do it. And that would be your identity that says cosine 2x equals 1 minus 2 sine squared x. So if we replace the left side of this equation with 1 minus 2 sine squared x, then the rest of the equation will still be equals negative sine x. And now we can see that we have 3 terms here. One of them is squared. That tells me that I'm probably going to end up factoring a trinomial. And so I'm going to want all of the terms on one side of the equal mark. And I think I mentioned before, whenever we're factoring with a squared term, it seems the most natural to have your squared term be positive. So let's take this negative squared term and move it to the right side so it can be positive. And we will also move this 1 to the right side, and that will make it negative. So that will give us 0 equals 2 sine squared x minus sine x minus 1. So this is a trinomial that we will factor by reversing the FOIL process. It's going to factor into two binomials. So 2 sine squared x is going to break down into 2 sine x times 1 sine x. Last times last made a minus 1. So the minus tells us that the signs need to be different, and the 1 tells us that we're going to need 1 times 1 here. Now let's add up the middle term and see if it gives us the middle term that we want. Outer times outer would be minus 2 sine x. Inner times inner would be plus 1 sine x. Negative 2 sine x plus 1 sine x does add up to negative 1 sine x, which is what we wanted. So we know that this factoring is correct. Now, since one factor times the other equals 0, one of these factors must equal 0. So we need to find out what values make 2 sine x plus 1 equals 0. And in a minute, we'll also need to find out what x values make this other factor equal 0. First, let's concentrate on 2 sine x plus 1 equals 0. So if we move the 1 to the right side of the equal mark and then divide both sides by 2, we'll see sine of x equals negative 1/2. Now sine values are negative in quadrant 3 and also in quadrant 4. And because the sine value is 1/2, we know that the reference angle for both of these solutions will be 30 degrees. For the quadrant 3 solution, a reference angle of 30 degrees would give us 210 degrees. And for the quadrant 4 solution, we would get 330 degrees. Now let's take the other factor and set it equal to 0. So if sine of x minus 1 equals 0, then sine of x equals 1. And that's only going to happen when the y-coordinate of a point on the unit circle is 1. So that would have to happen at 90 degrees. And now we're ready to write our solutions in our curly braces, but as we go we'll have to convert these to radian form because that's how they asked for the solutions here. So we've got x equals, curly braces, 210 degrees, which is 7 times 30 degrees, so that will convert to 7 pi over 6. 330 degrees, which is 11 times 30 degrees, so that would convert to 11 pi over 6. And then 90 degrees, we know, converts to pi over 2 radians. And that is the end of example 1. Let's get another example here. So this one says solve cosine of x equals sine of 2x for all exact solutions in radians. Okay, so again, we have a 2x argument here, and we need to replace this function of 2x with an identity. So if you look at your formula sheet, you can see that the sine of 2x equals 2 sine x cosine x. So now our equation says cosine of x equals 2 sine x cosine x. So notice that we have two different functions and they're multiplied together. So that tells us this equation is nonlinear in form. It is going to have to be solved by factoring. And that means that we need to have all the terms together on one side of the equal mark, and we need 0 on the other side. In this case, let's take the cosine x and move it to the other side. That would give us 0 equals 2 sine x cosine x minus cosine x. Now look at these two terms. They both contain a cosine x, which means we will be able to undistribute or factor out cosine x as a GCF. So that would give us 0 equals cosine x times parentheses 2 sine x, because cosine x times 2 sine x would create this term, then minus 1, because cosine x times 1 is cosine x. You can see that if I were to distribute cosine x through this parentheses, I would get this expression back. So this factoring is correct. And now I can say, since this factor times this one equals 0, one of them must be 0. So first let's take the cosine x equals 0. To find these solutions, we want to think about where on the unit circle would the horizontal coordinate equal 0. And that would be at 90 degrees and also at 270 degrees. Now for the other factor, when 2 sine x minus 1 equals 0, if we isolate the sine of x, we'll see that we need to find where sine of x equals 1/2. So we've done this before. We know that sine of x is positive in quadrant 1 and quadrant 2. So we're going to get a solution from each of those quadrants. We know from the 1/2 that the reference angle will be 30. So the quadrant 1 solution is 30 degrees, and the quadrant 2 solution is 150 degrees. Now to write our final solution set, we will convert each of these degree solutions to radian form, and we will also add our plus 2 pi n after each solution. So here we go. X equals curly braces. For the first solution, 90 degrees, we know that that's pi over 2, and then we will add plus 2 pi n. The next solution was 270 degrees, so that would be 3 times 90 degrees, so that's going to convert to 3 pi over 2, and then we add 2 pi n for that as well. The next solution was 30 degrees, so the radian equivalent for 30 degrees is pi over 6, so we'll write pi over 6 plus 2 pi n. And for 150 degrees, that's 5 times 30 degrees, so this one will be 5 pi over 6, and then we'll add 2 pi n for that. Now, before we go on to our last example, I do want to point out that for these two solutions, because they are pi radians apart, it's possible to write these two solutions as one and not have to have two separate ones. You can do it. I'm not going to require you to do it, and my lab also does not require you to do it, so I don't want to go into detail, but in case anybody is looking at this and saying, that was a long way to write that, there was a shorter way, you're right, there is a shorter way. And finally, here is example 3. So this one says, solve 2 cosine theta equals 2 cosine 2 theta for all exact solutions in degrees. Now, this one will be solved the same way as the first two that we did from this section. I just wanted us to have one more chance to solve an equation that involves a trig function of a double angle. So let's take a look at this equation together. The first thing I notice here is that both sides have a coefficient of 2. So why not divide both sides by 2 right off the bat? The reason we can do this is because 2 is just a number. It doesn't contain a variable. So you know that we could not divide both sides by cosine of theta, for example, but we can divide both sides by a constant. That's no problem. So now we have cosine of theta equals cosine of 2 theta. Okay, now you know from example 1 that there are 3 different identities that we can use to replace cosine of 2 theta. We want to choose the one that uses the same function we see on the other side of the equal mark, and that would be 2 cosine squared theta minus 1. So now we've got cosine theta equals 2 cosine squared theta minus 1. Again, this is a trinomial. We see 3 terms here. One of them is squared. So we know we're going to need to factor, and in order to do that, we know we're going to need all 3 terms on the same side of the equal mark. Let's bring this cosine theta over to the right side and make sure and write it as the middle term so that you can see how to factor. That will give us 0 equals 2 cosine squared theta minus cosine theta minus 1. Now, this is a trinomial that we hope to factor, so if it factors, it's going to factor into 2 binomials. 2 cosine squared theta has got to be 2 cosine theta times 1 cosine theta. And then since the last term is minus 1, we know that the signs will have to be different, and we know that the numbers will have to be 1 times 1. So now let's check and make sure that our middle term comes out the way we want it to. Outer times outer would be minus 2 cosine theta. Inner times inner would be plus 1 cosine theta. That does add up to our middle term, which is minus 1 cosine theta. So we know the factoring is correct. Now we can say, since this factor times this factor equals 0, one of the factors must be 0. So we want to find out where 2 cosine theta plus 1 equals 0, And then in a minute we'll find out where cosine theta minus 1 equals 0. Let's solve this factor first. So if 2 cosine theta plus 1 equals 0, when we isolate the cosine theta, we find cosine theta equals negative 1/2. So cosine values are negative in quadrant 2 and also quadrant 3. This 1/2 we know is the cosine of 60 degrees. So now we know that the reference angles are 60 degrees. That would make the quadrant 2 solution 120 degrees, and the quadrant 3 solution would be 240 degrees. When cosine theta minus 1 equals 0, that means cosine theta equals 1. So we're looking for the point on the unit circle where the horizontal coordinate would be 1, and that would only happen at 0 degrees. And now we are ready to state all exact solutions in degrees. So since we want to stay in degrees, we will add plus 360 degrees in to the end of each principal solution. So theta equals, curly braces, 120 degrees plus 360 degrees in, comma, 240 degrees plus 360 degrees in, comma. And then for the last one, we could write 0 plus 360 degrees in, but there's really no point in writing 0 plus because adding 0 has no effect. So for this one, we will just write 360 degrees times n. And I didn't leave myself much room to write, so I had to shrink my solution set a little bit, but we do need to write where n is any integer after our solution set. Okay, you guys, that's it. I hope I've given you plenty of examples to work with and copy. It will take you a little practice to get really good and comfortable at solving equations, but definitely do that, work through your problems, contact your instructor if you need a little point in the right direction, and we'll be glad to help you. Okay, good luck. I'll see you in the next section. Bye now.